Good evening. Um, Tonight is August 12th of 2020. It is now 10 o'clock p.m. Eastern Time, and so it is time for us to begin our bi-weekly lesson that takes place on Thursday night. So in tonight's lesson, we are going to go through lessons 4, 5, and 6, just kind of glossing over the more complex points, things that might cause confusion. I feel like in the last recording I did on lessons 1, 2, and 3, those concepts were a little bit more tricky because they involved a lot of definitions of words and explanations of significant figures, which could be discussed in its own lesson for more than an hour at least. But tonight's topics are a little bit easier to understand. So I don't think that this recording is going to go for nearly as long as the last one did. Last recording was a little bit under an hour. This one, if all goes well, we should be able to get this wrapped up in about 30 minutes or so. So without further ado, once again, lesson 4, let's click on it and see what we're going to be dealing with. Okay. It's logging me into StudyForge right now. Once again, StudyForge is the videos and practice questions that you're supposed to complete after each lesson. And almost there. Okay, here we go. So once again, I'm not going to watch the video. I'm just going to kind of fast forward through it. But you can see we've got plenty of practice questions down here that you can take time on. Watch the video before you complete this practice question so that you can pick out any details that are important. Okay, so if we fast forward through this video, this video is all about units and how useful they can be in our study of physics. So as I was watching this video in preparation for tonight, I noticed they basically take us through 4 or 5 cases where discussing units can be helpful to help us understand a particular problem. So I'm going to throw all of these examples up on the screen at once, and we're going to talk about each one one right after the other. Okay, so here are all of the concepts. So on the left-hand side, we have topics 1, 2, 3, and 4. So basically, the thing about units, I think we always take them for granted. You may have had teachers in your whole school career tell you, don't forget the units. If the unit's not there, it's gonna get marked incorrectly. But units, we don't give them enough credit for the usefulness that they provide us in solving problems. So this first number here, this first principle that we want to discuss tonight, says units can help find a formula. So if we know that velocity is measured in meters per second, we then can say that, well, it's because meters measures distance and seconds measures time, velocity should be equal to distance divided by time. Okay? Or differently put, velocity is equal to delta x divided by delta t. Okay? Now, d meaning distance is a lot more straightforward than seeing that delta x represents displacement, but that will come with time as we discuss displacement in future lessons. But the point is that anytime you're changing a distance, like you are when you're displacing an object, and if that happens across a certain amount of time or difference in time, that is velocity. So we just took units of velocity, and from those units, we came up with an equation. So that's what makes units so useful. The second useful thing about units is because only like units add, if you're noticing that you have 2 terms in an equation that are being added together and those units are not the same, then you know that your equation is probably incorrect, okay? So what I mean by that, if you take a look at this equation, Remember, we already set up above that velocity is measured in units of meters per second. Okay, so if I've got an equation for velocity, I've got two terms that are being added together here. Okay, now if we're going to be adding these two units together and ending up with v, which is measured in meters per second, that means that both of these quantities, v naught and delta x over delta t, both of these should also be measured in meters per second, because only like units can add. Okay, so that's another concept I thought would be useful for us to go over. Topic 3. This basically is kind of cool, a cool way of showing how formulas can be expanded and manipulated to make units appear out of nowhere. So for example, we know that the units of acceleration are meters per second squared. Okay, now if you were to take acceleration and multiply it by time, for example, if you took meters per second squared and multiplied it by the seconds, we would cancel, because we have seconds on the top and seconds on the bottom, seconds would cancel with one of these powers down below, leaving us with just meters per second. Okay, so by just realizing that fact, we now know that acceleration multiplied by time will cancel that seconds out and leave us with a single seconds unit on the bottom of that fraction. And remember, meters per second is the same thing as velocity. So we just figured out by playing around with units and a formula that acceleration multiplied by time gives us units of velocity. Okay, and using the same concept that we learned up here in topic number 2, because we can only add like units, velocity should be equal to two terms that measure velocity being added together. So here we have v naught being added to acceleration times time. We just proved that acceleration times time gives us a velocity, therefore we can add that with another velocity. Okay, and that brings us to the last topic covered on this slide. Okay, if you are solving a problem and you think you are finished, but your units do not match up with what the desired unit should be, then you can be confident that something went wrong over the course of the problem. So for example, if the problem is asking you to calculate a velocity, but when you do the math, your units are actually meters squared over seconds squared, you know that's got to be wrong, because that's not the units for velocity. Okay, so units can help us know when our answers are right. They can also help us know when our answers are wrong. Okay, now I've worked with students for the past several years, and one thing that I notice about high school students and college students is that we get pretty lazy when we're writing our answers down. And so let me just encourage you, always, always, always keep track of your units throughout every single calculation that you do. Sometimes it's not even enough to just put the units on the final answer. I would encourage you to get in the habit of putting the units down on each individual step of the problem, because believe it or not, most mistakes happen in the middle of the math. So if you're keeping track of your units constantly throughout the process of solving a problem, you're more likely to end up with the correct units and therefore the correct answer at the end of the problem. Okay, now the rest of this lesson is basically just example problems and demonstrating how these equations match up with our units. So I'm going to allow you to kind of look through those yourselves. One thing I do want to mention though, and I mentioned this in the last recording, once again, we're assuming you've already taken a little bit of physics at this point, but even if you're not totally up to speed on physics, introductory physics that is, if these formulas don't look familiar to you, I wouldn't be too worried about it, because once again, we're going to go over these again, but the purpose of showing you these is not to scare you into thinking, oh, I got to know these formulas already. The purpose of these formulas being thrown at you right now is to help you understand how the math works, how the units will actually match up with the quantities that we're trying to calculate. So I hope that's comforting to you. Okay, so that's lesson 4. Pretty straightforward lesson. The video was only about 2 minutes in length, but I just spent about 10 minutes going over it. So hopefully with the actual video that you're able to watch with my perspective on it, you'll get a solid understanding of what the lesson is trying to say. Next lesson, lesson 5, is called Physical Quantities, including Scalars and Vectors. Okay, so we're going to give this lesson a couple seconds to load, and then we'll do the same thing. We'll skip through the video and cover the high points. Okay, taking its time. Almost done. Okay, here we go. Okay, so this lesson is all about scalars and vectors. This is one of my favorite topics to talk about for as far as introducing physics is concerned, because vectors can be a pretty confusing topic. And when you boil it all down, vectors isn't really that complicated, but I feel like a lot of students get confused about it because it's such a simple idea that it kind of goes without saying. So why should we have to explain it? You know what I'm saying? So let's talk about it. And I hope you get as much enjoyment out of this as I do whenever I talk about vectors with students. So let's fast forward a little bit. I'm going to go straight to the definition of a vector and a scalar. Okay, so here's our first definition. I'm going to keep going a little bit forward. And okay, so here we go. There are two words that you have to know by the end of this unit, okay? The first is a vector, the second is a scalar. Now, vectors are quantities in math that possess two characteristics, okay? Those two characteristics are magnitude and direction, okay? Direction is easy to understand, but the word magnitude sometimes confuses students. Magnitude is just a fancy word for how large a number is, okay? So in the example that's listed here in the picture, we can see this signpost pointing to Calgary, which is 10 kilometers away, okay? So how many kilometers away is it? It's 10. That's describing how far or how big the distance is. So that we call magnitude, okay? Now the direction comes because this sign is pointing somewhere. It has directionality to it, okay? So by simply having those two characteristics of magnitude and direction, we can classify this measurement as a vector quantity, okay? That's all vectors need, magnitude and direction, okay? And the next thing is scalar quantities. Scalar quantities are probably what most typical students are used to dealing with in science and math classes. Scalar quantities, you'll notice, just have a number assigned to it. It's a pure quantity with a number and units. You'll notice that from this definition, we're missing direction. So really the only thing that a vector possesses that a scalar does not possess is direction, okay? So if you think about measurements that we make in science or in life that do not have direction, but do have size, the most common example shown in this picture actually is time, okay? So when we're measuring time, let's say that it takes me 5 minutes to wash my dishes from breakfast this morning. We can't really express time with direction. We can just describe how long it took for me to do a task. Therefore, time is a scalar quantity. Now, some might argue, well, time could have direction. I mean, suppose that something were happening in reverse time. So suppose that time travel were possible, and we could go backwards in time. Backwards is a direction. Couldn't that be a vector? Well, we're not going to discuss that because we operate in the real world where time marches forward. So time, it can only march forward. Therefore, there's not really a direction associated with it. Therefore, it is a scalar quantity. If you think about other scalar quantities that exist, if you tell Well, let's look at this one in the slide actually. Something's weight. So if something weighs 1 kilogram, that's not really describing any direction. It's just a number whose size is used to convey meaning. Okay, so that is a scalar quantity. Okay, and you can think of several examples of what a scalar is and what a vector is. I would encourage you to do so, just so you can kind of illustrate the difference to yourself a little bit more completely. Okay, so here are some more examples. I'm going to skip over these. Feel free to look at those yourself. Here's some more practice. Practice question asking which of these can be represented as scalars, vectors, or something more complex. Try that out. Oh, I don't want to reveal the answer though. I want you to try it on your own. Let's go to the next video in the segment. Okay, this next video is about two-dimensional vectors. Okay, so very first thing that I want to talk about with vectors in 2 dimensions, once we get past all this introductory material, okay, so very first thing that I want to talk about is with respect to vectors in 2 dimensions is how you draw them. Okay, so this video is very useful. It illustrates a good technique in learning how to draw vectors, and you basically need 4 things to do this. You need a pencil, a sheet of paper, preferably graph paper if you've got it, a protractor, and a ruler. With those 4 things, you can draw a vector pretty easily. Okay. Now, you can see in this picture that the very first thing this person is doing as they're drawing their vector is they're drawing a straight horizontal line with their pencil using the ruler. Okay. The reason they're doing this is because we need an x-axis. Okay. So this blue line that this person is drawing, that is our x-axis. Okay. I'm going to fast forward so we can show you why we're doing this in a second. Oh, and look there. They even labeled it as the x-axis. Okay. So once you draw an x-axis, the reason why that's useful is because then using a protractor and lining up the x-axis with 0 degrees in your protractor, you can then measure angles and pencil them in. Okay. All with respect to that x-axis. So for example, this example problem at the bottom of the slide here says, suppose we want to draw a vector that's 60 meters per second at 20 degrees. Okay. So what they're going to do in this animation, we already labeled our x-axis. We've already aligned our protractor with the x-axis at 0 degrees. You can see that 20 degrees is right here. Okay. So if you kind of draw a dot at about 20 degrees, you can see where that angle is going to go. Okay, it's going to be about this angle right here, 20 degrees. Okay, so let's fast forward and see what they do with that information. Okay, I skipped a little too far forward. Okay, so here you can see they marked a little dot at 20 degrees, just like I said they would. Once you do that, notice that from the very center of this drawing, this is the origin of our x-axis. Okay, so the next step after you've drawn your x-axis, after you've drawn your little dot that matches up with the angle you're interested in, the next step is to actually connect your origin with your dot you just drew. Okay, so we've taken away the protractor, we've taken away the ruler, we've drawn these straight lines, and you can see this is a very neat looking drawing of this angle and this vector. Okay, and you always want to make sure that you label things really good in your drawing. So this is the final product. We've got our angle displayed, we've got our number with its units. So all together, this represents a very nice vector drawing. Okay, all right. Let's see if they had anything else to say in this video. Not really. Okay, let's go to the third video in the segment. Okay, so this video talks about making scale drawings. So we're going to run you through the materials you need to do a scale drawing. So once again, you absolutely need a ruler, you need a protractor, pencils are a must-have, and some sort of graph paper or engineering paper is good to have as well. Okay, so this video segment is just kind of a repeat of what we just talked about how to draw vectors, but they're basically going to bring into the discussion how to make sure your drawings are made to scale. Okay, so I'm going to fast forward quite a bit. This is just a review. So they're picking an origin point, they're drawing an x-axis, they're going to pick an angle out for our vector. Oh, see, there's the dot. So it looks like they marked this one at about maybe 38, 39 degrees. If you look at that, see how it's kind of right between 30 and 40, but it's a little bit closer to the 40 side. So I'm going to say about 30, 37, 38 degrees. Okay. Next step they're going to do is they're going to draw a nice line connecting the center to the dot. They label their angle with the measurement there. Okay. And look, they even labeled it with its magnitude. So let's say that this vector was representing a velocity vector of 57 meters per second. Okay. Because you are the architect of these drawings, you can decide the scale that you want this vector to represent. Okay. So let's suppose, just for fun, that we say, okay, in my drawing, let's say that 1 centimeter in my drawing is supposed to represent 5 meters per second. Okay. So for example, if I'm drawing a velocity vector that's 57 meters per second that it's supposed to be representing, I can use this conversion factor right here to figure out how many centimeters that drawing should actually be. Okay. So if I say, okay, well, if I've got 57 meters per second that I'm trying to represent here, so 57 meters per second, I'm going to use a little bit of dimensional analysis here. Oh, and actually I'm going to do this a little bit differently. Meters per second. And I know that for every 5 meters per second, I have 1.0 centimeter. You can see that using dimensional analysis, if you multiply your velocity vector by this conversion factor, the units meters per second will cancel, leaving you with units of centimeters. Okay, so if I times 57 by 1 divided by 5, I'm going to get an answer. It's going to be about 11 point something. I don't have my calculator with me, but it's going to be 11-ish. And we're going to check our answer because they're going to solve this for us in the video. But I'm thinking it's about 11-ish. Okay, and so you can see, if I fast forward a little bit, oh, looks like my work is covering up the answer. Let me move this stuff out of the way. Oops. Okay. Oh, yep. Looks like it's about 11.4 is what they got. Okay. And looks like they did it the same way that I did. They just did a little bit out of order, but that's okay. We got the same answer. So yeah, basically just you are the master of your drawing. So with the scale that you choose to use, you can calculate how long your vector should be to match up with the scale that you selected. Okay, so that concludes lesson 5, I believe. So let's go to lesson 6. And we've already hit the 25 mark of our time together today. So I promised we wouldn't go too long tonight. I was hoping to keep this under a half hour. So I think we're getting pretty close to being done though. Okay, so here is our next lesson loading. Don't forget to do those practice questions, guys, after you watch the video, because those are really what's going to help you prepare for your quizzes as well as for your AP exam. Oh, and another friendly reminder, don't forget to get the Princeton Review Cracking the AP Physics 1 exam. We mentioned that in the last recording, but you will need that before we hit Module 2, which is coming up pretty quickly. All right. Okay, so this last video is going to describe for us how to add vectors together. So remember that at the very beginning of our recording tonight, we said that you could only add quantities together that have the same units. And I think we used velocity as the example. It's kind of the same thing for adding vectors together. If you're adding vectors together, they have to have the same units for you to be able to add them, okay? Now, adding vectors together, here's a sample problem. If we've got a woman walking 4 kilometers at 30 degrees north of east, and then deciding to walk 3 kilometers due north, and we want to know what's her displacement from our starting location, we've got two vectors that we need to talk about. Vector 1 is this first part of the problem, where she's walking 4 kilometers at an angle of 30 degrees north of east. The second vector we need to worry about is this one, where she's going 3 kilometers due north. Okay, so if you watch the animation, they're drawing the vector, just like we showed you two in the last video. They drew our blue vector, which represents the second portion of this woman's journey. And if we want to add these two vectors together, what you can do is take the two arrows and link them together, okay? So you can see that on the left side, we drew the two vectors separately. On the right side, we're drawing them together, but we're drawing the second vector coming out of the arrowhead of the first vector, okay? This is how you draw vectors being added together, okay? So we've drawn the two legs of the journey connected to each other, as you can see. And if we add these two vectors together, the way to do that is just to draw a new line that goes from the starting point of the first vector and connects with the final point of the second vector. And we call this green vector our resultant vector, okay? So once again, a resultant vector is just the sum of two other vectors, okay? And what you can do is you can measure the length of this resultant vector, and then using the scale that you designed as the architect of your drawing, you can convert that size into an actual quantity that makes sense in the context of the problem, in this case, kilometers. But you would need that conversion factor that you selected to be your scale. So you can see they're walking us through this. They're taking that ruler, they're measuring the length of this resultant vector that we drew. Okay. And then after we measure the distance of that vector, we measure the angle that it makes with the x-axis. So you can see it's between 50 and 60-ish. I'm going to guess 55 degrees. And the answer, you'll see, oh, I was close, 55.33 degrees. So you can see that our resultant vector is about 6.08 kilometers at a direction of 55.33 degrees north of east. Okay, so main takeaways from this slide are that you got to add vectors by putting them connected to each other, head to tail. So the red arrow was connected to the blue arrow, and then the sum of those two vectors was drawn from the starting point of the first vector to the ending point of the second vector. Okay. All right. And that is pretty much it for that segment. Let's keep going. This is our last segment we're going to talk about tonight. All right, so this video talks about how to subtract vectors, which is very similar to how to add vectors. So suppose that you want to subtract a vector from another vector. And they give you a nice example in the video. I encourage you to watch it because it illustrates the idea very well in a problem that's a little bit more complex. So basically, in this video, we've got two vectors. Our first one was drawn in blue. Our second one is drawn in red. Okay, and you can read in the problem. We're looking for what is the vector displacement. Okay, so suppose that we were supposed to do this by subtracting vectors. Okay, the rule for subtracting vectors is written up here in this red box. It says subtraction is done the same as addition except the subtracted vector is turned around into its exact opposite. That is, the direction of the vectors is in the exact opposite direction, 180-degree change. Okay. So suppose that we're doing this between these two vectors. I'm subtracting one from the other. To see this in practice, here's kind of a detailed look at what our vectors look like before we do any math with them. So our blue one is going due north at 90 degrees from the horizontal. Our second vector is 30 degrees below the horizontal, okay? So suppose we want to subtract them. Well, the very first thing we got to do, as the rule up in the red box says, you have to turn one of the vectors around into its exact opposite. You can see that down here. We took our dark blue vector up here. We did a 180-degree turn and drew it the same length in that opposite direction. Okay, so this vector right here is the vector that we are going to end up adding with the red one. Okay, so once again, the rule for subtracting vectors: take the one you're subtracting, flip it so that it's going in the opposite direction, and then add it with the other one. Okay, so if we keep going forward, you can see that we're doing the same kind of technique. We took our red vector, and then we drew it coming out of the arrowhead of the first vector, okay? Just like we talked about a few minutes ago. So because these two vectors are connected end to end, we can draw the resultant vector from the starting point of the first vector going all the way to the ending point of the second vector. And they're going to do a much better job than I could, since they have these nice straight line tools for them. But you can see they're bringing their ruler in, they're drawing that vector from start to finish. We're going to measure that using our scale. We're going to translate that into a quantity that makes sense in the context of the problem. And we're also going to estimate the angle using a protractor. Okay. So here you can see the scale. We're saying that each centimeter is about 4 meters. So using that scale factor, this vector, which was 4.33 centimeters when we drew it, it's actually going to correlate with a 17.3 meter distance. And then using the new angle, you can see up here that drew the new angle in red here. And we can see that that angle is about 60 degrees below the horizontal x-axis. Okay. You can see 17.3 meters at 60 degrees south of east is our final answer. Okay. And then the rest of the video is just another example. So I don't want to spend too much time on it because I want you to be able to study it without me giving it away. But you can see that we're basically taking two vectors. We're going to subtract them. So notice at the beginning, the blue vector is pointing up. But because we're subtracting vectors, we're going to flip it around and make it go down. And then we draw the two vectors connecting to each other from head to tail. And then we draw a resultant vector going from the start to the finish. And there we go. So we can see the distance it represents in the problem. We measure the angle with a protractor, and the problem is done. So that kind of wraps up what I wanted to talk about today. So just to review, first thing we talked about were how units can be helpful in coming up with equations and checking your work to make sure you're doing the problem right. We then talked about what the difference is between a scalar and a vector quantity. We said that vectors have magnitude and direction, whereas scalar quantities only have magnitude. We then learned how to make vector drawings using a ruler, a protractor, a pencil, and a sheet of graph paper. And lastly, we learned how to do a little bit of vector math on a graph. Okay, so we learned that when you're adding vectors, you have to draw them head to tail, and then draw from the starting point to the ending point a straight line so that you can measure its distance, convert it to a distance that's representative of the problem using a scale factor, and also use a protractor and measure the angle. We then talked about vector subtraction, which is basically the same thing as addition, except you have to flip around one of your vectors and make it go the opposite direction. Okay. Now, my last thing I want to mention, I'm going to be a little honest here. Drawing vectors, I have not done that much, either myself or with students. And the reason for that is because shortly we're going to teach you how to do this without even really needing a drawing. Drawings are always helpful, and I would encourage you to keep making them. But the math behind how we can do this without making a drawing, it's pretty straightforward geometry, okay? So we will get to a point in this class where you might not feel the need to make a drawing because you can kind of picture it in your head. You can plug it all into an equation and figure it out yourself. But I don't want you to stop drawing vectors until you feel absolutely comfortable with how to draw them, okay? Okay, that concludes what I wanted to talk about tonight. So I'm gonna end this session right now. Please email me if you have any questions. And thanks so much for watching, and we will see you in the next recording. Bye-bye.